Okay, good morning, good afternoon, good evening, wherever you are in the world. I'm happy to happy to have you join the Amphenol webinar series. I'm Sam Kosis, the Director of Standards and Technology at the Amphenol Communications Solutions Group. And I'm going to talk today a little bit about some interconnect trends that are shaping tomorrow's data centers. Amphenol has a very broad portfolio of solutions spanning several markets: automotive, industrial, data center to telecom. We're going to focus today mostly on what's happening inside of the data center, but it is important to recognize that our broad portfolio in different markets helps us find and enable technologies that help groups across different market segments as we look to evolve electrical interconnects, optical interconnects, cabling solutions to different markets. So things that are popular in one area often find their way into other areas as time evolves and the technology matures. For the past several years, Amphenol's motto has been, we are enabling the electronics revolution. And generally, we're the ones pushing copper solutions to the next generation. We've actually also been developing a fairly significant footprint in the optical space as well. We currently have over 13 businesses in our division supporting optical solutions. We're talking end-to-end optical solutions, meaning a combination of transceivers, but also fiber patch cords, the cabling, wire management, and the enclosures that go into deploying the fiber optics in the data center. Again, supporting a diverse range of markets from both industrial, ruggedized, military aerospace type applications, as well as traditional data center where optics has been a mainstay for several years now. Our optical footprint has really continued to grow, specifically in the module space, to help complement our strong product offerings in the electrical channel and market segments. So I encourage you, if you have some time, to look at each of these pages, do some research on what each of them offers, how they complement each other, and if you have any questions, we're happy to help direct you to the right group and the right representative to help get you a solution or answer to your question. So specifically, today's focus is going to be, all about the artificial intelligence, machine learning, and a special attention generally on high performance computing market. And the rack is really becoming the unit cell for data centers, replacing traditional servers or network switches. Amphenol's broad portfolio of products, it creates almost a one-stop shop for exploring these rack level solutions. Things like bus bar and power management, general mechanics of how things go into the racks, also reimagining backplanes, connectivity between the boxes inside of the rack with copper wires or active components. We find that connectivity and flexibility is really the key, as the racks are then linked together to form what is often referred to as computing clusters or pods. Our rack scale solutions really help combine the efforts of many businesses and teams worldwide. So we're working hard to connect the factories and supply chain elements around the world with our global manufacturing footprint. We'll go a layer deeper now and kind of talk a little bit about the components that go into these end-to-end solutions. And end-to-end here, we mean, from the chip to the port. And the port may continue on with passive copper interconnects or some type of active electrical signaling, and we'll talk a little bit about what each of those means. Or it could mean some type of optical translation where you can go from kilometers to even further reach outside of the data center. So our expertise and development really starts with enabling connectivity to get out of the chips, out of the CPUs, out of the custom ASICs, and our socket technology helps do that and provide flexibility at a way for platform developers to be able to improve the yield and overall fit of their products in their ultimate platforms. escaping the ASIC has been a very big challenge, and we'll talk about some of the challenges as we go to higher data rates in the slides to come. But we're also finding that these near chip interconnects are becoming more popular as architectures evolve over time. So we've done some things in the optics space with sockets to support near package optical modules, or NPO. We've done some things in the same footprint to be able to support copper interfaces from those ports with a near package copper NPC connector. And all of that helped build out and really stabilize our overpass product line, which effectively provides a way to mitigate concerns with printed circuit board materials by introducing cabling to get to different modules inside of a chassis or connect to ports to go from chassis to chassis. We're in our almost third generation of these products, starting with micro link over, a very low profile but broad interface to the board, moving on to our DensaLink family of products, and then currently our UltraPass series is providing the most dense bandwidth performance solution in the market today. From those interfaces, we then go to pluggable ports often. The front panel and the density of the front panel has often been the key to providing connectivity within a rack or rack to rack. And our I/O connectors range from SFP through QSFP. We're showing here in the pictures the profiles of the cages with their heat sinks for cooling and thermal management. And we really own and support the customization for the system needs and the module needs and how they come together at the port. And it's been one of the areas where our team has really excelled in finding the right solution for the customers based on their overall system needs. Now, once you get to the port level, we get to an interface that will require extending over some reach. So the best TCO, or total cost of ownership, is typically with copper cables. They've been around for a number of years, and we continue to find ways to integrate copper solutions into the rack architectures. We also have a fairly broad portfolio of active optical cables. And really, in the last 3 or 4 years, we've grown a lot to extend our optical module capabilities. Ranging initially from SFP products and supporting the fiber channel community. 2 years ago, we had a very strong launch of our 400 gig products with the QSFP-DD form factor leading the way. And in the last 24 months, we've really come a long way with our OSFP product line, building out solutions supporting 400 gig, 800 gig, and now 1.6 terabit. We do this with retimers, but we've also been leading the development of linear pluggables, or LPO modules, and supporting some of the ways that folks are trying to reduce power as they increase the scale and complexity of these systems at the rack level. And power is a huge concern, and it's been a huge concern, getting worse as we've gone faster and more dense over the years. So this is a picture from the Ethernet Alliance showing some of the evolution of the data center in terms of time, going back over the last decade plus, as well as the aggregate bandwidth that we've been able to get out of these chips, and ultimately looking at the total power that we're getting from those solutions. And what we've seen is the power demand is not going away. It continues to increase. And the cost of these new technologies is becoming just as critical as the attempts to try to save power. So our pluggable I/O form factors that I showed on the last slide are now driving upwards of 3 amps per pin in some cases. And we find that the two biggest culprits of the power consumption in the chart here are really the core SerDes power as well as the optical module power. And so a lot of work has been done to demonstrate feasibility for putting these solutions together and just being able to continue the increase of bandwidth and speed. But we also need to be sure if there's a possible way for us to reduce power that we're attempting to do that. And so we can't really do anything regarding the SerDes power if we're trying to support passive copper channels. The increased SerDes power, the complexity of the SerDes equalizers are really what's helping to continue to enable the support for copper cable and passive copper links at today's data rates. But the area that's almost as problematic is the optical module power. And so there's a lot that's being done to figure out different ways to potentially cut some corners, take advantage of the capabilities of the SerDes architectures that can be more effectively using different solutions, different technologies to help reduce that power at the module level. This is another chart from the Ethernet Alliance talking about some of the evolution that might drive us away from pluggable optics. So in this case, we'll look at the picture and start at the graphic on the bottom, which is very similar to the end-to-end channel I showed 2 slides ago, and really creates the topology that we used for the chart on the previous slide. You have your core switch package with your switch die that's driving printed circuit board or some electrical channel over some length to the point where you can get to an interface where you can have a pluggable optical module. And one of the opportunities for reducing the power would be to bring that optical translation closer to the switch, closer to the ASIC. And so there've been a couple of generations where people have looked to go and try to do that. The first maybe being onboard optics, where you bring that optical module inside of the box, inside of the chassis, and ultimately create a more reduced electrical stress channel as you go from your switch ASIC to your optical module. And continuing with that trend, if we look at the picture in the top left, we could further integrate the optics with the switch package and the switch die. And this would provide the lowest burden of electrical stress on the channel going from the switch die to the optics. And that's being referred to as co-package optics, where the switch ASIC and the optical module reside on the same package. So these are techniques that are being deployed and considered as we try to figure out ways to reduce the power. As the electrical channels get smaller in each of these pictures, the power is actually being reduced primarily here where it would be most beneficial from the switch ASIC package and switch ASIC die. However, in practice, if that same switch ASIC is meant to support passive copper cabling over front panel pluggables or backplane solutions, you really need to maintain that capability, that power consumption, the complexity that's in the switch ASIC to even have a chance to make those links work. So another way that people are thinking about pursuing power savings is to reduce the power consumption at the optical module level. And that's where linear pluggable optics, or LPO, comes into play. And this is an area that, because of our strong portfolio and history in the electrical space, we feel like the LPO solutions help complement some of our other electrical product lines in determining a solution path that enables an ecosystem that supports low cost, high performance copper, as well as long reach, low latency optical solutions. So if we stick with the copper elements for a minute here, there's a few terms that I think it would be helpful to just align on as we think about the copper space and where it's evolved over the years. As we've continued to go faster and go over further lengths, we've actually had to reduce the maximum length that we can achieve as we've gone to higher data rates. Historically, everything was with the top picture, direct attached copper, and this provided a fully passive connection path between two chips, likely in two separate boxes within a rack or potentially in a neighboring rack. But as we've gone to faster and faster data rates, it's been harder to achieve the performance necessary to maintain that physical reach. And so we've come up with a couple of different copper-based cabling solutions, the first being active copper cables, where if we look at the link now from a directional point of view, the transmitter on the left goes through the same electrical channel to a pluggable port, but on the other side, where it plugs into its secondary port, there's a linear equalizer there to help give it some signal conditioning, potentially some gain, to help get that electrical signal the last mile to the chip on the right. And we found these to be very helpful in closing the gap between physical reach limitations without compromising significant power or complexity within the host platforms as well as within the cable assemblies. The third picture is what we'll call an active electrical cable, where these cables end up actually looking more like pluggable optical modules. They have DSP or CDR-based retimers inside of the cable assembly. The switch ASIC drives an electrical channel to the pluggable port, and then it gets retimed and retransmitted across the copper cable to the other side, where it's retimed and retransmitted again to go the last third of the link. And these cables help provide, obviously, even more physical reach benefits. If you're limited by the channel because you have to maybe drive an electrical channel from your switch to your port, that's extremely stressful. These devices are very helpful. And those devices today often come with a lot of diagnostic capabilities that are also very helpful for our end customers. So we continue to explore all three of these options. Each of them has trade-offs in terms of cost, power, and performance that need to be considered when you're designing and developing a platform. But having each of these options at your disposal can be very helpful in terms of being able to bend but not break your architecture when it comes to maintaining compatibility with copper solutions. So we have this ecosystem built up for supporting copper solutions, and now we're looking for a way to integrate optical solutions, be able to go over much longer distances, right? If we're limited to a couple of meters with copper solutions, maybe 5 or 6 meters, even with the active copper, active electrical solutions, there's still going to be a need to go over tens of meters, hundreds of meters, maybe even 500 meters inside of a data center. And for that, you're going to need to use optics. So these ports here, pluggable optics, look very similar to the way that the copper cases work, except inside of those modules, you start with that DSP and you go over an electrical to optical conversion, go over your fiber interconnect, and then do the same thing on the other side, converting back to electrical and going to your far end receiver. So what I want to talk about here is really how LPO, or the linear aspect of this, is defined, right? So the DSPs in these modules tend to consume the most power, and this is the primary area we try to target in looking at power reduction. And some of that can be done with process node improvements or more efficient component choices. But the other way to do it is to look for ways to architect the solutions that can remove these DSPs altogether. So if we were to remove one of these DSPs, potentially here shown on the transmit side, this is what's called LRO, where you're just retiming on one side, not the other side. And you could do this on either side of the link and still maintain the power savings. It's been proven to be most effective to do this on the receive side. So LRO often stands for linear receive optics in terms of where the module is linear and where it's retimed. Now, if you're able to remove the DSP on both sides of the link in both modules, now we're in a situation where the entire optical interconnect is linear, and this is exactly what a linear pluggable optics solution looks like. You're taking advantage of the capabilities of the DSP, the SerDes, the equalization on either end of the link, and you're doing that electrical to optical conversion without any retiming of the link, and ultimately providing the biggest power savings for your end platform. So this helps set the stage for sort of the ecosystem of different interconnects that we can use when we're thinking about how to architect solutions within a rack or a couple of adjacent racks, creating these compute clusters. One of the things that's become apparent is what is the ultimate power difference between these is going to drive how attractive these solutions are in the overall market. And I think looking at it in terms of watts is generally the way that we do in the interconnect community. However, most people in the architecture world tend to think of it in terms of picojoules per bit, and they look at these large platforms in terms of aggregate bandwidth and traffic going in all directions, and they're looking at ways to save power, and the metric they use is picojoules per bit. So what I've tried to do here is convert what we have in terms of per end power at each data rate for each of these interconnect types. And I've used the 8-lane module, the OSFP module as an example here. I've converted all these numbers to the picojoules per bit to try to get a rough approximation for the attractiveness of the different solutions at the different data rates as we look to define what might be the best or optimal interconnect to support scale-up architectures to create these compute clusters. So obviously, as we are at slower data rates, 25 gig per lane, there's not much need to go to active copper cables or active electrical cables. We're able to support with passive copper cables easily 5 meters of reach, and we can go from top to bottom of the rack and probably rack to rack without much concern. Anything in tens of meters or hundreds of meters, you're still going to go with optics anyway. And for the most part, the diagnostics and the robust ecosystem, the power at those data rates, LPO is not, linear pluggable optics is not really a necessity at that stage of the game. Now, overall, what we're hearing coming out of a successful and very eventful OFC a month and a half ago is that for scale-up architectures, the target is typically below around 5 picojoules per bit to support the rack level scale up. So you can see as we're getting ready to ramp and support 224 gigabits per second per lane, we're left with only a few options that can give us that picojoule per bit that's sub 5 and really the target for these scale-up architectures. Things are continuing to evolve and improve as process nodes improve and components become more power efficient. And so ultimately, this is where you can see the active electrical cables still coming in a little bit more power inefficient compared to LPO, which has really been a driver for us in investing and continuing to invest in supporting the LPO opportunities. Obviously, there's a strong push to get some type of optical solution that can get to sub 5 picojoules per bit. And clearly at this point, we're probably not there yet, but we're continuing to evolve and develop partnerships with our supplier base and work on ways to continue to make that improvement to support some of the architectures that are going to be needed in the coming years for high performance computing. Now, the interesting thing about LPO or really any of these electrical links is that it all comes down to the channel and how best you can support an electrical performance with the channel that you have. And I had mentioned it a few times, but one of the things that is really helpful to start with is having a very capable SerDes that has great compensation algorithms, some advanced signal processing like MLSD, multi-level sequence detection. And these are now standard really at 224 gigabits per lane. So we know that copper will win as long as it can keep pace with the density and data rates. And so having that complexity inside of those SerDes gives us a foundation for being able to go and try to figure out a channel topology that can support passive copper. So that leads to the other aspect that's very important as we go forward and determining what a high quality channel looks like. And it starts with choosing the right topology, the right connector interface, and really asserting control over the areas where you can control and maintain guidance between the interfaces with impedance transitions or different interconnect solutions that can give you the highest quality channel. So if we dig into some of those interconnect options a little bit, the pluggable module family across the top is a graphic that the EA has proudly promoted. Now, this really just shows the broad evolution of pluggable solutions from 1-lane SFP modules through 8-lane and now 16-lane modules with OSFP XD. Each of these provides different aggregate lane densities, and each of these modules has been pushed every generation to be able to meet the performance, the electrical performance at the interface level on a per lane basis. But there's still reasons to think about employing other interconnects as your architectures evolve. Cabled hosts, these near package copper or co-packaged copper solutions might help mitigate some of the issues with printed circuit board losses, or potentially BGA or socket breakout if that's a bottleneck, if you are able to put the interconnect right on the substrate. The backplane style interfaces help significantly improve the density and aggregate bandwidth of the solution, and pairing that with cabled solutions helps create a very new paradigm with cable backplane that allows you to really do some cool things, connecting modular components inside of your rack in a way that has not been done historically. And all this broad spectrum of solutions helps to enable a ecosystem of interoperability. And as we think about what that means for optics, if you have an LC connector or an MPO connector that plugs into any of these form factors above, on the other side, provided your pair matched or lane matched, you're able to provide that interoperability point at the optical interface where you might not be able to at the pluggable module interface. So really cool things continuing to emerge and support the evolution of these interconnect styles as we've gone to higher and higher data rates. Now I spoke a little bit rather on the performance of each of the components. And one of the things that we continue to try to push every form factor to is being able to achieve the performance targets of the interface that's needed at that particular data rate. And so what I've tried to do here in one graphic is show the evolution of our products as we develop 10 gig SFP through our 1.6T OSFP products. And this is really remarkable, I think, when in terms of bandwidth, the form factor itself has stayed essentially the same, but the internal designs of the connector, the tolerance control, the manufacturing processes have all improved significantly, where we used to be limited to sub 20 gigahertz bandwidth. We're now exceeding 60 gigahertz bandwidth with the connector interfaces at 224 gig. This is truly, I think, a remarkable feat, and I think continues to be paired well with other great advancements in the industry, test and measurement, continuing to keep pace with our ability to create interconnects that have higher and higher bandwidth. We're finding ourselves now at the limit of today's vector network analyzers and test equipment as we try to capture the real limitations of what these interfaces can do. So we take this connector interface and we need to put this as sort of the benchmark of our channel as we put these together. And when I talked about channel optimization and some of the things that we can do or can't do, I tried to divide it here into two separate categories. On the top, we have these transition points that are purely physical. They're either mechanical or something permanent in the structure. And these transition points typically are the most detrimental discontinuities in the channel. The package BGA is often fixed at a particular pitch, and that pitch will determine ball size, which leads to a requirement on the via size and the pad size. These are things that we can do the best we can, but ultimately we're likely left with a discontinuity that we have to overcome in the channel. On the other side, these orange arrows point to areas in the channel where we're a little bit more flexible. We have the opportunity to make some specific design changes or design requirements that can help mitigate some of the issues we have at the areas of the blue arrows. So if you have a very low impedance coming out of your BGA on the far left, and you're trying to match to a particular impedance that you know you're going to get into with your pluggable IO connector, that area in between, whether it's a PCB transmission line or some type of overpass cable solution, you can drive a little bit of customization into making that transition a little bit more gradual, helping to eliminate some of the discontinuities that are going to affect your channel. And so the other arrows just kind of point to other opportunities where we can do sort of that same thing. Certain areas we're going to be limited by size, but other areas we're going to have more flexibility to be able to support that. Now, in terms of the channel optimization, I tried to look at a real example, taking in the time domain all of those same areas that we had in blue and orange on the previous slide, and looking at what that looks like across a spectrum of time in a channel. And so you can see a lot of times we have the sharpest transitions in those blue areas where we're sort of fixed because the pitch is fixed or the manufacturing process limits us to certain geometries in the structures. And so it's really important to identify what these fixed or flexible structures are to help figure out what the most optimal thing that we can do in the orange areas where we have more control. And so one of the things that's come out of recent optimization efforts is sort of an understanding that as we go to higher and higher data rates, it may be more beneficial to move the impedances that we can control down a little bit away from 100 ohms differential, closer to 92 or 92 and a half ohms, to better balance things that we see coming out of BGA vias, printed circuit board materials, and ultimately that leads to overall better performance channels because we're able to minimize the total discontinuity impact through the channel. This is one of the things we really try to avoid here, right? The minimum and maximum, when you have those two very close together, this is a key discontinuity where we really want to focus attention to try to mitigate anything we can control to try to minimize that to improve the channel performance. Some of the other areas are going to be a little bit harder to identify and control, but in the areas where we have the mechanical interfaces, these are obvious candidates for places where we can do some improvements. And so again, we look at this range, you know, somewhere between 90 and 100. As you look at your structures in your channel based on the interconnect options that you choose, you may find that your target impedance for your channel might be somewhere in between based on the topology and the components that you're choosing. So what this looks like is we kind of put it all together and things that we can do architecturally. The picture in the upper left is a picture I've been using for the last several minutes to kind of talk about these different topologies. And then as we try to put some of these near package copper or co-packaged copper solutions, now we start to get away from traces in the printed circuit board and move towards an interface that gets directly to copper cable to mitigate losses or maybe provide some connectivity between boards in a rack or in a chassis that aren't physically connected on the same baseboard. And then when we do that, we're also able to maybe interface with different style solutions. Like instead of going to a front panel pluggable, if your particular platform or appliance is several U rack units, you can maybe use some type of backplane or cable backplane solution to provide a cleaner path between your two devices and ultimately get more performance out of it. So one of the things that's becoming more challenging here is really keeping track of the compliance points, where the interoperability point is or where the break point is for determining channel quality, component quality, is becoming increasingly harder to manage. And obviously we're all also dealing with struggles as we get to higher and higher data rates. We may solve certain things in one area, but other areas are still very difficult to improve and overcome. jumped ahead there. So, as we think about bigger picture protocols and the way we architect these systems, um, for artificial intelligence, high performance computing type systems, we're kind of left with a tug of war between protocol solutions for this space. On one hand, you have Ethernet, where they're going to give you the fastest data rate historically. On the other hand, you have a native compute style protocol with PCIe, which is giving you very low latency, very low overhead with error correction, at the price of having to be very clean with your channel and probably limiting yourself in terms of reach, right? So what I've shown here in these slides, or these tables here on this slide, sort of an evolution of the projects in parallel, Ethernet on the left and PCIe on the right. And what's shown is sort of how we've moved from different per lane data rates, different modulation schemes. Everybody has migrated now from NRZ modulation to PAM4. And then you can sort of look at the evolution of the total insertion loss end to end and how that's impacted the overall reach target of the passive copper cable. So the reach target here is for a purely passive copper cable, or the DAC type, right? And what we see is that for the active copper cables, pretty much at each one of these, when you have that linear equalizer, you're able to double the length. So you can go for 100 gig, you do, instead of 2 meters, you could do 4-meter copper cable. Now the active electrical cables can do obviously pretty much the same thing, doubling the reach. In many cases, we're able to get to 6 or 3 times the reach, 6 meters with the 100 gig per lane. And this general estimation holds pretty true in the PCIe space as well. So this is just something to consider when you're trying to balance performance, interconnect type, and physical reach targets that you're trying to go and target. Now the data center networks, what we're looking at here is, again, primarily an expansion within the rack or neighboring racks. So historically, these pluggable ports have been used to connect top of rack switches into this architecture of aggregation layer inside of a data center, and then it goes outside the data center through routers with the same port structures. But everything in this high performance compute area is really driven on expanding the connectivity and the compute capacity within the rack. And so everything within these green arrows here, kind of looking at the ways we're architecting the server, storage, and accelerator elements, figuring out ways to cram as much compute into these units as possible. And so a good example of kind of how this has been done in the past, historically, years ago, the NVIDIA platform, the DGX, was a advanced server platform that had a traditional server connected through a backplane to a GPU tray that provided the acceleration and the scale up capability. And over time, NVIDIA had donated and contributed that design through HGX to the Open Compute project. And that evolved to, again, another way for providing scale up capability within an accelerator cluster that could connect to basically any type of server. In all of these architectures, though, you're limited to 8 accelerators, as shown here on the screen. And that's largely due to power constraints and physical reach limitations. And so what the Open Compute project had done several years ago was put these interface ports where you could use the pluggable I/O, whether it's passive copper cables, through these expansion modules, to be able to connect accelerators within different boxes or different racks together. And so that's where the term scale out came from. Scale up was everything that was sort of native in your box, and scale out was the way that you connected to different boxes. But even this has become somewhat obsolete in the last few years, and people are continuing to look for ways to take the core network elements of a server platform, compute, memory, acceleration, and figure out ways to package that in a rack to provide you the most dense and highest aggregate bandwidth of compute capacity. And now that is being referred to as the scale up network. And then once you've reached that optimal point for your network, scale out continues to connect multiple iterations of those network elements to create your overall network cluster. Now, inside of the compute nodes, ways that we're looking at doing that is obviously going to drive more need for interconnect. So the server platform's evolving has been great for us because it provides an opportunity for more innovation at the interconnect level, exploration of different form factors and different technologies. And PCIe has done a great job of promoting different internal cabling solutions as the server was modularized to support different storage elements, add-in cards, and just different ways of connecting these boxes together to make the servers more capable. And at the same time, in recent years, there's been a strong push to extend that even further to be able to support optics. And so there was initially a great convergence of opportunities for PCIe and optics because of this opportunity in high performance computing. Historically, storage applications had been the primary use for PCIe cabling as an alternative to SAS or SATA solutions. And CXL came along, and over the last 12 months, we've seen actual prototypes and first products for pooled memory applications. And so that's become another area where PCIe cabling is starting to emerge as a front runner. And then ultimately, as I described, all these different ways of connecting compute capacity, connecting those accelerators or GPUs to the CPUs, or even just connecting these accelerators together. There's a number of different standards efforts within the OIF for energy efficient interfaces or compute optical interfaces that all would benefit from very low latency, low power, as high bandwidth as you can achieve with those limitations as the source of the fabric interconnect. And so all of these three market opportunities really found themselves centered around PCIe as a potential opportunity for the protocol solution here. And so a little bit just quickly about PCIe basics. PCIe is a little different than Ethernet in that there's some directionality involved and there's some challenges in terms of how they specify channel performance metrics and where the compliance points are. You have your root complex on one side of the link and your endpoint on the other. And pretty much everything in between is flexible for the platform architect to put together a channel that works for their platform. There are some elements that you have to live within in terms of requirements, in terms of electrical budget, and really the only requirement, hard requirement, is first bit error rate, which is really just the probability of a first bit error occurring at the receiver pin. So multiple occurrences don't typically degrade the bit error rate that's reported in that statistic. But ultimately, these types of solutions, the flexible solutions here, provide the opportunity to use lower FEC error correction and be able to provide some more flexibility at a much more attractive point for platform developers. So how could we integrate this with optics, right? We can, instead of thinking about it from the electrical budget, we would think about it more from that BER target. But even then, most of the modules are designed to be able to support a certain electrical reach on the other side of the link, the line, the host side. And then on the line side, they're designed to support a certain reach on the optical side. So there's definitely some more requirements that need to go into formulating the structure around PCIe-based solutions. And right now, what's being done in the PCI SIG is pretty much an electrical specification with some enhancements to be able to be friendly to optical implementations, but not necessarily interoperable. And I think that's an important distinction as people are looking to choose between Ethernet-based solutions like UA Link or UEC Ultra Ethernet versus PCIe. There's a lot of flexibility, a lot of benefits of sticking with PCIe, but it does come at a expense of owning that flexibility and how it manifests into potential errors or vulnerabilities with interoperability. And so on the right, I just kind of showed some of the ways that PCIe is doing something to provide compliance and interoperability between vendors. The add-in card and the chem interface has been a mainstay for PCIe solutions in terms of being able to prove that your retimer or your host device are compliant to the PCIe standard. But as far as cabling goes, we're pretty much left with the electrical requirements that are inside of the red dashed lines in the picture on the bottom. And even then, it's up to platform developers to figure out how that solution fits into their system performance and to make it work for them. So there's still a long way to go, but I think there is some encouraging things happening in the industry. At OFC last month, we had a demonstration of PCIe over optics. We brought together a number of different partners to create a very extensive demo that not only provided multiple data rates, PCIe 4, PCIe 5, but connected different appliances and network elements, some test fixtures together to be able to run actual applications and go through the challenges with link bring up, link recovery, which are really going to be the key details that need to be ironed out for something like this to really take off in the broad market. So what we did here was we ran some lightweight artificial intelligence type algorithms from an Intel CPU, pulling from different accelerators and materials that were in the storage space, but doing everything over different interconnects from copper to tens of meters of fiber to 80 meters of fiber. And this was interesting because there's a large debate concerned around the latency of the overall solution and how sensitive we are to being able to do these compute challenges without driving a latency budget that would cause retries and kind of blow up the link from a specification perspective. And we were actually able to find that the algorithms, the benchmarking that we did with 1 meter copper and 80 meters of fiber produced the same results, the same time to get the result, which is really encouraging about saying something about the overall latency sensitivity as we try to push these things together. It doesn't take away from the fact that we do need to provide some more framework for interoperability and how to break that down at a port or a module level. But it does show with all these partners coming together that there is an opportunity and an interest for the ecosystem to develop based on this type of protocol for these applications. Then I want to go back to the linear pluggable space and kind of talk about some of the challenges that we've had to overcome really with testing and how to gain confidence that these solutions are deployable and going to be serviceable with different topologies that might be out there in your appliances, right? And so we took a representative depiction of a top of rack switch. So we have a number of different interface paths from the chip to the module, and ranging from maybe 6 dB all the way up to 18 dB. So we're able to see whether more reflective, shorter channels are causing the problem or longer, more lossy channels are causing the problem, and figure out where the sweet spot is and what we can do with the device to be able to cover the solution space for both. All of these linear type solutions in the optical space are going to be very engineered to start as we try to figure out what the solution space is, and then we can build off interoperability and compliance requirements at different interfaces to help gain confidence at the end user level, but also provide some breakpoints for opening up the ecosystem of suppliers to different places in the link. So this is an exercise that we did at 800 gig, and we continuing to look to repeat this for 1.6 terabyte to help give us confidence that these solutions are compatible with our copper profile or copper products, but also give us a feel for how well they're going to perform as we migrate to the next generation of performance or of data rate expectations. This is just a quick summary of what those results are. Again, the BER at the end of the day is typically how we measure the overall performance of the link. And with all of these cases, we were able to see when you got the most loss in the system, typically pushing beyond what is a standard chip to module interface where you would design a module to have a retimer. We've been able to get a very good link performance with the LPO modules in this case. And so this is something that we're looking to try to replicate as we go to higher data rates. And we look forward to working with partners and interested users to try to put this together. Now, as we push to the next data rate, I want to finish with just kind of talking a little bit about where we see some of the challenges and the limits here. This is a CT scan of the mechanical interface. So that picture I showed before with the improved bandwidth from 10 gig connectors to 200 gig connectors, it's these types of structures that we really had to exert a lot of control on and figure out how to best put these things together in a way that's going to give us reliable performance mate cycle after mate cycle. And so what we see using OSFP as an example, today's tolerance loop and the dimensions that we have give us about a 56 gigahertz bandwidth. And we think that with tighter tolerance control, the timeline this project potentially would have to move to go to the next generation of products, looking at something beyond 224 gigabits per second. We can probably get to something that's like 84 gigahertz bandwidth, continuing with the same types of control mechanisms that we've had, a paddle card interface on a contact like shown in the picture on the left. This becomes sort of the limit for pluggable I/O. And so I think it's important to just recognize real briefly that there is likely going to be a limit for pluggable I/O. And now what that means in terms of where does the rest of the ecosystem and the topologies go? There's a big debate about modulation and what that means for the Nyquist frequency. So I tried to organize where we are today with 224 gig and look at the different modulation schemes, whether you're PAM4, PAM6, or PAM8, in terms of their associated Nyquist frequency. And so if we have an 84 gigahertz bandwidth limitation with the OSFP interface, it pretty much seals the deal for what the modulation would have to be for 448 gigabit per second, just purely based on the fundamentals of that interconnect interface. Now we are doing some things to try to further improve that, maybe look at other form factors, things that aren't exactly backwards compatible, but what we do see pretty consistently is that at 200 gigabits per second per lane, there's two major bottlenecks that need attention. One is at the package, the BGA breakout, and we're trying to mitigate that with some of our overpass solutions mounted directly on the substrate. And the other is the front panel interface, where we're trying to do some things to help get that bandwidth as close to 100 gigahertz as possible to give us some flexibility in terms of modulation choice, but also provide some margin in terms of performance that our customers are going to need as they try to deploy these links in volume. And we'll end here, but I do think that if you have an interest to continue on and discuss this, to reach out to one of our FAEs or contact us directly, and we're happy to kind of walk through some of the things we're thinking about and new technologies we're exploring to help us get past these hurdles. So as I leave here, a couple of bullets just to kind of end on. There's certainly a need for new innovative interconnect solutions to support these applications and to do so at a very fast rate. And how that determines interoperability is likely going to change based on the definition of scale up or scale out in your particular deployment or the deployment that you're playing within. And it might not mean the same interconnect solution is going to work for each one. So there's a number of different trade-offs to consider when deploying the different interconnect styles, moving from overpass cables to printed circuit boards, different backplane solutions. So it's another area where our broad portfolio of technology is really one of our strengths here as we try to provide our customers with a path forward to these challenging problems here. So with that, I think we're almost up at time. I'll turn things over to our moderator to see if there's any last minute questions.
Sam, I did send you 2 questions. Did you want me to read them, or do you want to go ahead and just review them?
Yeah, let me, all right, so the typical length, yeah, I think we covered that one, you know, with the slide that showed the different physical reach limitations. Typically, you know, if you think about it in very general terms, passive copper cable normalized to 1, ACC gets you double, AEC gets you 3x. And then how does temperature affect the 800 gig LPO? Yeah, so you know we're continuing to explore different cooling options, but in general, we've found the LPO performs very favorably compared to some of the active electrical cable alternatives. Air cooling is still very much in play for these types of modules. We haven't seen a specific reason that temperature would drive somebody away from LPO. But if there are any specific concerns, we'd be happy to follow up offline, maybe with something more detailed.
Thank you. Those were the only 2 questions we had.
All right. Well, I definitely thank you for your time today, and again, hopefully you've learned something or enjoyed the content. And you know, we look forward to tackling these challenges in the ecosystem together. And it's an exciting time for our industry, and we're happy to be very much a part of it and in the center of it. So thanks again for your time, everybody.